Linear vector quantizations are used to classify patterns. It consists of output units and each output unit represent a specific class. The unit represents the class with the unit weight vector as the reference or codebook vector. This is a special case of competitive net using supervised learning. Now, if you think about the KSOFM, Kohanan self-organization map, this is based on again competitive learning rule. It is based on the competitive learning rule. So KSOFM is also based on the competitive learning rule, and this LVQ is also based on the competitive learning rule. But difference between KSOFM and LVQ is that LVQ is supervised learning. This is supervised learning, but KSOFM is unsupervised learning. This is the basic difference between KSOFM and LVQ. In both the cases, we are using competitive learning rule, but LVQ use supervised learning and KSOFM is unsupervised learning. When the training process is complete and the LVQ NEET classifies the input vector whose weight is very close to the input vector in the same class, then it reduces incorrect classification by conducting LVQ boundaries. LVQ is supervised learning algorithm that looks like KSOFM net while KSOFM is an unsupervised learning algorithm. Now let us consider in LVQ, I will consider some parameters, and these parameters I will show you structure of this LVQ. So let us consider X is the input. X is the input training vector. X is the input training vector, and this X it is it has elements like x1, x2, x3, then xi, then here it is x n minus 1 and x n. So these are the vectors present in elements present in input training vector. So the size of input training vector is I, it is varying from 1 to n. So this is the size of input training vector. Similarly, as it is supervised learning algorithm, here training data set is provided with targeted output. So let us say T. T is nothing but the target output. T is the target output vector. T is the target output vector, where this target output vector it is varying from T1, T2, and I will show here this is T3, then TK, TM minus 1 and TM. So here this total number of targets are M, where variable is K, K it is varying from 1 to M. So how many classes are there? How many output classes are there? Any answer? How many output classes are there? Huh? There are M number of classes. Okay. Then there is link or weight between the input and output nodes. So these weights are given by Wj. These are the weights connecting between hidden layer to output layer. So these are the weights connecting between hidden layer to output layer. So these are the important parameters. Then again, related with these weights, these are the weights between input and hidden layer, or these are the weights between hidden layer and output. But there is one more parameter which is called as Cj, where Cj is nothing but bias of hidden unit. So these are the four important terms. First one, X, it is the input training vector. Then target output vector, where input they are varying from 1 to n. Target output they are varying from 1 to m. These are nothing but the classes, because this LVQ it will classify input training vector into classes. This is the supervised learning, and it is based on the competitive learning rule. Now Wj these are the weights, and Cj these are nothing but the bias. Now here I will draw structure of this LVQ. So I will show here structure of LVQ. Now, as I said, there are n number of inputs. So these are the inputs. I will show here x1, then xi, and xn. These are the n number of inputs. And I will show here these are the hidden nodes, the input nodes. So these are the input nodes. So here this is x1, xi, and xn. So here it is. So these are the inputs. As I said, these are the n number of inputs. It is varying from 1 to n, where I is the variable. Then these are connected to the output nodes. So I will show here, these are the output nodes. So y1, yj, or here yk, and here it is ym. So this is the ym. Now here there is connection between input nodes to output nodes. Sorry, there is one connection here. This is the weights connecting between input layer to output layer, and these are the bias of output nodes, output units. So this is the connection. Then I will show here connection between these input and outputs. So this is the connection with y1, then yk, and then ym. Again, I will show here connection between xi to yk and ym. Similarly, here connection between xn, yk, and ym. So these are the connections. Now here, one more important thing. If y1 is the output node, then output is y1, then this is yk, and this is ym. So these are the outputs. And the difference between LVQ and KSOFM is KSOFM is a unsupervised learning, where LVQ is supervised learning. So therefore here targeted data is provided. So this is the targeted data T1, TK, and TM, where this is the targeted data and this is the actual data calculated by using your LVQ. Now here these are the input nodes, this is the output node. Then there are weights of connections, as I said, showed here Wj, weights of connecting between input layer to output layer. So I will show here these weights. So it is connecting between 1 to x1, input from x1 to y1 it is written as 1 1, it is written as wk1, it is written as w1f. So these are the weights of connection. Similarly, I will show here weights of connection between ith node to 1. So it is w1i, this is w2i, sorry, wki, and this is wmi. It's similarly connection between third node or nth node to the output node. So I will show here these connections as w1n, wkn, and wmn. So these are the weights. So here these are the weights, and this is the structure where these are the input nodes, weight of connections, then output nodes, output, and this is the targeted data. Then there is one more input which is called as bias. Now here I will show this bias. Bias here it is the C, it is related with 1. So I'll write here weight of it is C, sorry, C10. Similarly here it is CK0, and this is CM0. and this weight bias of weight value of this bias is nothing but 1. So it is equal to 1 and it is equal to 1. So this is the structure of LVQ. This is the structure of LVQ. This is the structure of LVQ having input nodes, output nodes, and these are the connections. Now here there is similarity between these LVQ and KSOFM, but difference is only targeted output is given, or this is the supervised learning. Now let us start with the, is there any doubt in this structure? This is the very simple structure. Is there any doubt? Hello? This is the very simple structure. Just input node, output node. These are the weight of connections, bias, and output, and this is the targeted data. This is called a structure of LVQ. Now let us start with the algorithm of LVQ. So let us start with the step 0. Okay. In step 0, first initialize the reference initialize the reference vector using following steps. So initialize the reference vector using following steps. So first step. Now in this case, take m training vector from the set of training vector as a weight vector. Use the remaining vector for a training. Now in this case, let us consider x is the input training vector. X is the input training vector. So let us consider there are, now these are the elements. These are the elements. This is not size of vector. Now if you show here size of the structure, then it is like this. X here it has total x1, x2, x3 up to xn. Correct? So this is the element of first vector. So there are n number of elements. So I will show here. Let us consider this is the first one. Then again x2. How to show x2? x1, x2, x3 and xn. Correct? So these are the elements of second vector. So here let us consider there are a total s vectors. Correct? So x1, x2, x3 up to xn. Is it correct? Now we can say that the size of this vector is x s by n, where s these are the number of vectors and n these are the number of elements. Now in this case, initialize the reference vector using following steps. So I will show. First step is take the am training vector m training vector from the set of training vectors as weight vectors weight vectors. Use the remaining vector for training. What is the first step? Take the m training vectors from the set of training vectors as weight vectors. Use the remaining vector for the training. Now here, as I said, let us consider there are x1 to xs. x1 to xx. These are the number of vectors, number of input vectors. Out of this number of input vectors, let us consider, I will show here x1, x2, then xm, and then xs, correct? So take this first m number of training vectors as a weight vector, correct? And remaining input vectors, are for the training. Are you getting this one? So weight vector, it is defined from the input training vector. Is there any doubt? Hello? Are you getting this one? How to define weight vector? Weight vector is nothing but the input training vectors. If m, why we are taking m? Is there any idea? Yeah, there are m number of classes. So therefore, we are taking m number of weights from the input training vectors, and remaining input training vectors, they are used for the training. Is it correct? So this is the first step where we are taking m number of input training vectors. Then second step, assign the initial weights. Assign the initial weights. Then use k-means clustering algorithm. For assigning these weights, you have to use k-means clustering algorithm. Then next one, set initial learning rate. Set initial learning rate, which is nothing but eta. So this is the first step where initialize the reference vector using following steps. So this is the method. Then step 1. Step 1. What is the step 1? Do step 2 to step 6 if the stop condition is wrong. Stop condition is wrong. So repeat the steps 2 to 6 until you will get the stopping criteria. Then next one, step, this is the step 1. Step 2. Step 2. Do step 3 to step 4 for each training input vector. Now what is the condition? We will repeat the step 3 to 4 for the every input vector. Now in this case, as I said, if there is x1, x2, xm, then xm plus 1, xm plus 2, it is up to x. Last number is x. Here, what is the value of x? 1, 1 2, x1 2, uh, x1 to s, correct? Because these are the vectors, these are not elements. This is not I, correct? This is s. Then in this case, we will define x1 to m as a weight vector, correct? And these are the input vectors, correct? So repeat step 3 to step 4 for each training input vector. So you have to repeat this step 3 to step 4 for xm plus 1, xm plus 2, xm plus 3 up to xs. Are you getting this one? So repeat these steps for xm plus 1 to x plus s, xs. Is it correct? So you have to repeat these steps. You have to repeat these steps. Then now what is the step 3? I will show here step 3. Step 3. Calculate Euclidean distance Euclidean distance for I 1 to n and j is equal to 1 to m. Now it is 1 to n. 1 to n, these are the number of elements, and 1 to m, this is the number of, what is 1 to n? 1 to n, if you remember, 1 to n, these are the number of elements, 1 to n. And what is 1 to m? What is 1 to m? No, 1 to m, these are not number of outputs, these are the number of weights. These are the number of weights, correct? Not outputs. Oh, as I already said that this is the weight vector where size from 1 to m, 1 to m, and 1 to I, 1 to n. This is the number of elements in one input vector, and 1 to m, these are the number of weights, correct? So calculate Euclidean distance for I 1 to n and j 1 to m. So here I will show how to calculate this Euclidean distance. So it is given as dj is equal to summation. Here there are two conditions, I tends to 1 to n and summation j tends to 1 to m. So here it is xj minus wij square. Are you getting this one? So this is the calculation of Euclidean distance. Then find the winning find the winning unit index j when dj is minimum. Are you getting this one? How to calculate winning unit? Winning unit calculated by using this dj. If dj is minimum, then this is the winning vector. We have already calculated it is in KSOFM. If you remember, one numerical is taken on KSOFM. In this case, minimum distance or distance is calculated, and if distance is minimum, then this is called as a winning vector. So similarly here, when dj is minimum, this is called as a winning vector. Now it is numbered as j. Is there any doubt? Okay. Then next step, step 4. What is step 4? Update, update the weights on the winning unit Wj using following conditions. What is the condition? If T is equal to Cj, what is T? T is nothing but the targeted data. Then Wj new is equal to Wj old plus eta into x minus Wj old. So this is the equation. How, if this is the winning vector, correct, then update the weight. How to update weight? Wj new is equal to Wj old plus eta into x minus Wj old, where x is the input vector, correct? So already this equation is solved, or it is used in KSOFM. Now if another condition, if T is not equal to Cj, then Wj new is equal to Wj old minus eta into x Wj old. Now what is the difference? Here, if it is winning node, then it is calculated by using this equation where this is plus, and if it is loser, then it is calculated by using minus. So this is the difference between weight updation for winning node and loser node. Then step 4, sorry, this is the step 4. Then step 5, reduce the learning rate. Reduce the learning rate, eta. And last step, step 6, test for stopping condition of the network. States the stopping condition of the network. So this is the training algorithm of LVQ. Here I will repeat once again. First, we have to initialize weights. To initialize weights, we will consider input vectors from 1 to m. After initializing this one, we will initialize the learning rate. Then after this one, step 2, repeat step 2 to step 6. Step 2 to step 6. If condition is wrong, if condition is true, then stop. Then step 2, we will repeat step 3 to step 5 for all the input vectors. So here step 3 is calculate Euclidean distance and find out the winning node. If winning node is calculated, then update the weight. This is for the winning node and this is for the loser node. Then step 5, reduce the learning rate. How to reduce learning rate? It may be n eta is equal to eta into 0.5. It is reduced by half. So again, last one, test the stopping condition of the network. So this is the very simple algorithm. Already it is used in KSOFM. So is there any doubt? Yes, please. You can ask if you have any doubt. This is a very simple. You have to remember that LVQ is like KSOFM. In LVQ and KSOFM, competitive learning rule is used, while LVQ is supervised learning, but KSOFM is unsupervised learning. Now in this case, let us consider these are the parameters and draw the structure. The structure is very simple. This is the structure of LVQ, and after getting this one, you have to just write down this algorithm. Correct? So this is the very simple part of linear vector quantization. Is it clear? Okay, I will share this PPTs or this is the write-up. I will share with you. Okay. Okay. Thank you.